Hi, welcome. In today's video we have a Commodore 64, a PCB prototype board, some sensors, and we're going to play with them. So let's have some fun. If this is your first time in the corner, then welcome, it's nice to see you. If you've been here before, then welcome back, and you know what to expect. So the idea for this video came from another YouTube channel, Josip's Retro Bits. Now I'll put a link to the video that inspired me in that corner, I think that corner. Check out the channel as well, it's very well worth subscribing. This is a prototype board. It plugs into the user port and it comes from our favourite PCB manufacturer. It's a shared project. More about that a little bit later on. Regular user port connector. We're going to solder this onto here, and this is then going to give us a springboard and a platform for doing all of our experiments and messing about. Now, I'm not much of a machine language programmer or assembler programmer, so what Josip did with this, and he used this little sensor here. I'll give you a link to all of these things in the description. In my case, they came from the Pi Hut by and large. I'm sure there are other outlets for them. So this is a temperature sensor. This is what they call a one-wire sensor, and this is the same as the one that Josip used. It comes with a little series resistor. You do need to program it in assembler, and to show that I'm probably going to nick his code, so then we have the classic little analog temperature sensor. This is a thing, it looks like a resistor in a sort of TO92 type package. This one is made by, or comes from Adafruit. We're not going to be able to use the user port for that because this is of course an analog device, so we're going to make use of the analog input of the joystick ports and play with that. This comes from Pimeroni. It is a BME 280 temperature, pressure and humidity sensor. A really nice environmental sensor that is ideal for indoor monitoring of temperature, pressure and humidity, or even outdoors in a suitable enclosure. I believe this is an I2C interface. So it's going to be interesting. Can we make the C64 using the user port? Can we make it talk to an I2C device? Because if we can, that opens up a whole realm of other I2C devices. If you saw my LEDs video a little while back, you'll know that a lot of those are I2C, and so we could play with that. And then this is an M5 device. This is a ENV3 unit. Again, it's a temperature, pressure, humidity. Again, it's a temperature, pressure, humidity device. And I think the interface for this is a different one again. So, yeah, we'll play with that. So some of the features of this prototype board. We've got the edge connector here along the bottom and on both sides. Now it's clearly labelled. This side is pin 1 through pin 12 and this side is pin A through pin N, and that means we know which way up the board goes because 1 to 12 is on the top and A to N is on the bottom. All of these come out to these pins, these holes here. So this is A1, B2, C3, so it's easy to wire stuff up. We don't need to worry about whether we're wiring to the top or the bottom because all the pins come out to here, and then each of these pads is on its own, so we will need to wire it up just like we were using, you know, sort of ordinary breadboard. So that's fine. Then at this end we have 2 edge connector pads each side, and then in the middle we have 1, 2, 3, 4, 5 switches. So this is an edge facing tactile switch, and they just plug in like that. And then these 4 pins here control what goes to the switch, so we can have buttons and switches and do nice things like that. So this is a very versatile little board. Okay, the first thing that we need to do is solder the edge connector to this. Now these edge connectors are actually quite wide, so if you hold that on, you'll see there's a big gap. You'll see there's a big gap between the boards. So what we have to do is basically fold it over. And eventually that will basically make contact. So we can solder that. What I've done is I've put another connector on this end just to hold the board up so that it is more or less flat. That way it's not going to be at an angle when we solder it. So I'm just going to tack the ends first. There we go, we can look at that, check that it's level, it looks to be level. Okay, so that is on. So just to double check, I am going to write top on the top. So that way we know that the board is going to be on the right way around when we plug it in, and we can start building circuits. So looking at the programmer's reference guide, we have got the details of the user port, and there it is, 1 through 12 at the top, A through N at the bottom, directly connected to a 6526 CIA chip, and on the next page we can see all the connections. So pins 1 and 2 we've got ground and 5 volts, we've got a reset line, and then on the top we have basically a serial port, and then on the bottom we have some handshaking and port B of CIA number 1. So we've got basically 8 bits to play with. We can have some fun, and then it tells us how to use it. So we need to decide where to put our bits. What I've done here is I've put some M3 screws, or bolts rather, through this so that when it's plugged in it rests like that on the table and it doesn't put any strain on that connector. I would use nice proper spacers, but I didn't have any of the right size, so bolts will have to do. Right, the bits that we have: the sensor itself, which is a waterproof temperature sensor. It's a 1-wire interface, which is a computer controlled serial thing. It's done by timing, quite fast timing. It's something like 100 microseconds that it needs to set up and send the data, and it's serial, and you have to do it within the time. So it's a assembly language program rather than a basic program, which is why we're going to be nicking Josip's code, because he's already done it, and why reinvent the wheel, at least for this bit. So roughly speaking, we've got our sensor here and 3 wires that come out. This is the white wire, this is the yellow wire, and this is the red wire. The red wire goes to 5 volts, the white wire goes to ground, and the yellow wire is our signal, and that is going to go to pin D, which is on the CIA PB0. So it's the low order bit of the output input port. And in the bag that didn't come out, but is provided with the kit, is a 4.7K resistor, and that goes between the data and 5 volts. and the effect of that is going to be as a pull-up, so that this pin will naturally be at 5 volts unless the signal drives it down. So I've got a few extra little bits. This is a simple terminal block. The reason for this is, and it's going to go in here halfway down the board, because it's going to go in here so that we can screw this in here, because I want to reuse this board for all the other little experiments and projects that we're going to do. And then this is going to sit, let's say here, that's going to sit on the data line, basically to isolate it from this 4K7 resistor, so that when we reuse the board for something else, then that pin is not going to be tied up to 5 volts. There we go. I've rather crudely written the colours of the wires on the board here, red, white, yellow, just so that we know that we're going to put them in the right way around. For a more permanent solution, a better label would be ideal. So, screw terminals. Resistor goes between yellow and red, which is 5 volts in signal. The red wire then goes to underneath pin 2, which is 5 volts. The white wire goes to pin 1, which is ground, and the jumper, which is the yellow wire, goes to pin D, which is PB0. So all we need to do now is find a screwdriver, and that's going to fit, I think. Yep. So this is taped up. Let's hook it up. So that's our interface made. Let's plug it into the C64. There we go, and let's run some software. We have the setup connected to the computer. So everything's wired up. Here's the sensor connected into the little terminal block. I've also put a probe in there to the oscilloscope. Not measuring anything at the moment because it's not switched on. That's just monitoring our data line. I'm taking it from the connector there. And on this SD card I have a copy of the program that Josip wrote, and that came down from his GitHub. So let's just switch it on and see what happens. Now you'll see that the oscilloscope has gone from 0 volts to 5 volts. That is because the 4K7 resistor is actually, there we go, that's because the 4K7 resistor is actually pulling it up to 5 volts. And here we have the Commodore 64. On the SD card we've got the program DS18B20.prg, because this is a DS18B20 device. Now this is machine language and it loads at 4096 decimal, so therefore we have to load it 8,1. I'm going to load star because it's the only program on the disk. 8,1, and that just saves a bit of typing. Right, and to run it, sys 4096, that runs the code, the machine language code, at 4096. And immediately you see temperatures, and if we look down at the oscilloscope you can see the one wire serial signals being sent and received. And the temperature in my office at the moment is 26.5. And you'll see from the thermometer, hopefully you can see from the thermometer, there we go, it's not far off it, at least according to the thermometer. 25, 26, 27, so 26.5 is about right. So the other standard test that we have to do, I've got a glass with some ice in it. Let me stick the temperature in the ice, and immediately we can see that the temperature on the probe is starting to go down. This is running real time about as fast as it will go, as far as I understand, because from Josip's video this is basically in a tight loop. We're down to about 3 degrees, 2 degrees, 1.5. It may not get all the way down to 0 because there are some gaps between the ice cubes. That looks like it's about as low as it's going to go. Okay. So the next thing is going to be my coffee. You can see, Commodore mug. So let's dunk it in the coffee and see how cold I've let my coffee get. And immediately it starts going up. We're up to 29, 30 degrees, 35, 37, 40. I've no idea how hot a cup of coffee actually is. 45. I'm going to guess it's going to go a little bit higher because it's slowed right down. I'm not sure we'll get to 50, but we'll see. I'm not sure we'll get to 46 actually. So about 45.5 degrees, it's starting to go down again now. It's obviously the coffee actually starting to cool down rather than the sensor warming up. So let's take it out, and that's going to come back down to room temperature, and I am going to drink my coffee. So what I'm interested in now is where we can take it from here. As the software is written, it's basically a continuous reading of numbers, but it doesn't do anything with those numbers other than display them on the screen, and I don't think that is particularly interesting. It's not particularly useful anyway. So what I think we want to have is a data logger, and what we're going to do is we are going to log the temperatures that we read from here over a period of time, and we're going to store them on this. That'll be fun, won't it? And we can do. So I've hacked Josip's assembler a little bit, and I've got it open on the screen, and we'll just take a quick look and see what I've changed. Okay, so primarily what I wanted to do was make it one shot, so that when we call it, it just reads the sensor and then returns the value. And I want it to return it to basic. So what I've done, first thing that I've done is changed the load address from 4096 to 49152, which in hex terms is going from 1000 to C1000. You'll notice that I've cleared out some of these variables. That is because most of these are to do with converting the number and printing them out on the screen, and I don't want to do that because I'm returning the value to basic. So the next change that I made is val. This is the value that is being read from the device. It's being read from the device bit by bit, and it is converted into a byte in val. Now, in the original, val is at A0 in 0 page. This is being used as the current time, TI dollar. And since that is kind of important to what I want to do with the temperature reading, in other words, when I read a temperature, I want to associate it with the time that I read the temperature at. And so it's kind of important not to lose that. And consequently, I've moved val to somewhere out of the way. And that is to location FB, which is reported as being unused. The next thing that I did was take out the clear screen, because I don't need to clear the screen because I'm not using the screen, at least not in the machine language. And inside the loop, we send 44, which is the command to read the temperature. And then Josip has these two delay 1000s, which is basically to give the thermometer time to convert the value into its internal buffer or at least copy the value into its internal buffer and ready for us to interrogate it. But there is, and I'll bring this up, in the DS18B20 documentation, and there's a link to this in the description, but it says convert 44 hex, single temperature conversion, data stored in 2-byte temperature register in the scratchpad memory, and it goes back to low power idle. We're not using parasite power mode, so we don't need to worry about that. If it's powered by external supply, master can issue read time slots after the convert T command, and the DS18B20 will respond by transmitting a 0 while the conversion is in progress and a 1 when the conversion is done. So I thought I would give that a go, and instead of doing these long delays, which gives the sensor time to do it, I don't know how long it's going to take to do it. So I've copied the original read bit command without copying the result into val. Basically, I just took out the bit that copies the result into the val variable and builds up the byte. And so this just comes back with a single bit, and we look and we compare it. Is it a 0 or is it a 1? Now, if it's a 1, then we go back and we just keep going around this loop. Tum-ty-tum-ty-tum. And if it's a 0, then we can go... I said that wrong, didn't I? So we read the bit, and if it's a 0, then we go back round here and we keep polling it until what we get is a 1. And if it's a 1, then we continue on. And then this is as per the rest of the original, except we do not go back round the loop. But what we do is this. And you may have seen give AYF is up at the top here. It's address B391. And this is a routine to convert an integer value into a floating point value and store it in the floating point accumulator. And the integer value is 2 bytes in 2's complement, which strangely enough is exactly what we've got from the sensor. So we copy the 2 bytes, H byte and H byte plus 1. These are the bytes that we've read back from the sensor, and we put one into the Y register and one into the A register and call this, and that's going to copy it into the floating point accumulator as a floating point number, and that is going to be the return value from us calling the user function. So looking further down, I'll read scratchpad routine. Yeah. Okay, so we send the BE command, which is read scratchpad, and we do everything exactly the same. All the way down here, we calculate the CRC, and at the point at which Josip's original starts to print out, convert it into a screen representation and print that out on the screen, we say, okay, that's enough, we're done. And this does give us a bug, because if you look here, we look at H byte plus 8, which is the last byte that we read, which is the CRC value. We compare it with the CRC that we've calculated, and if the result is not 0, then we terminate. Now, in Josip's routine, that jumps over all the printing out stuff, and so it ignores basically values that failed the CRC, and we just see the correct values on the screen. But this ends the routine, and if the CRC is correct, it also just ends the routine. So basically, regardless of whether the CRC failed or passed, we just end the routine, and that is a bug. We need to do something about a CRC failed, and we'll come back to that later on. But for now, we're going to see what happens as it stands. So, and everything else is exactly the same. So that is what we have done, and let's go and have a look on the C64. So we're back at the 64, The one little change that I've made to the hardware is to add a couple of extra wires so that I can put an oscilloscope probe onto the data pin. So that goes, the orange one is the data pin and the white one is ground. And that goes to the oscilloscope, which is sitting at 5 volts because of the pull-up resistor. So let's look at the program. So I've written a little basic program. It's called highly originally BAS, just because that makes it easy to type. This is Josip's original code, the assembly version, which runs at hex 10004096. And this is my version. I've just called it a .bin because it's code that I don't want to directly run, and that is going to load at hex C1000. But we're not going to directly load that. We're going to go into the... Whoops. I always do that, make that mistake. It's a bit slow. One day I will get around to installing Jiffy DOS. I have bought the ROMs. I just haven't got around to it yet. So, very simple little program. This is a little thing here that stops problems with chaining programs. When we load stuff from within a program, it can potentially cause problems and it can cause it to restart. And if it tries to do that, then this A=1 thing will mean that we don't spend all our time just sitting here reloading the binary file. So we get the current time, stick it in TI dollar, then we load our binary file and we load it ,8, ,1. So that's going to load it where it's in, where it's meant to be, which is C1000 or 49152 in decimal. And then we're going to call it, and to call it we're going to use user, and the user function passes control. It does a jump to the address that is in 785 and 786. So what we're going to do is we're going to poke 785 with a 0 and 786 with 192, and that is going to be the address C1000. So it's going to jump to our routine at C1000, and it's going to return that number, the temperature that we saw that it put into the floating point accumulator. It's going to return that, and remember it's a 16-bit integer, and that is going to go into T%. Then I am going to calculate the actual temperature in floating point from this particular value, and we need to understand what this is doing. So we have a 16-bit 2's complement value integer. So that means it's 2 bytes, which is 4 nibbles, and this one, and this one are the integer part of the value of the temperature, and then this is the decimal part. Now, because it's a 2's complement value, we don't have to worry about converting that into normal values, because conveniently enough the C64's internal integer representation is 2's complement. So because it has values from -32768 to +32767, and that is stored as a 2's complement number. So when we look at T%, it's automatically already converted back into normal everyday numbers. So all we have to do is handle this. And to do this, we have 4 bits. So to convert this into an integer, we shift that left by 4 bits, which is the same as saying divide by 16. And when we divide by 16, we actually get this as the decimal. So it all works out. So we just divide this by 16 and that gives us our floating point temperature in Celsius. And that's great, but the problem that we then got is that this decimal value is actually quite high precision. So it's going to be, say, 25.1234. Now, maybe sometimes 4 digits of decimals is going to be useful, but I think for most of the time, with a temperature reading, we're going to be quite happy with 25.1. And so we want to knock that off. And to do that, what we do is we multiply it by 10 and take the integer of it and then divide it by 10. So basically that's going to knock off this. It's not going to round it, it's just going to knock it off. So that is a point of potential inaccuracy, but we need to be aware of that. So then the next line, line 20, that is just splitting up the time string into something that has got colons in the middle of it. So 15 colon 10 colon 10 as being the time at 10 past 3. But I haven't actually used that at the moment. So I just, in line 25, trying to move the cursor around left-handed and not getting it very right. I say at current time, then the temperature is TE, and I go back to 10. So this is just going to go in a loop and it's going to show the temperature each time that it goes around the loop. So let's run it. It'll be a little slow the first time because it has to load the machine language. Current time is 22:43 and 0 seconds. So there it is, it's reading the temperature. And just so that you can compare that, hopefully you can see that the actual temperature is about 26 degrees according to the thermometer. And if we have a look down at the scope, we can see the signal actually being transmitted on the one-wire interface. Okay, let's just stop this for a moment. You can see every now and then there is a wrong value. That would be fixed by probably by better checking of the CRC and actually doing something about having a failed CRC value. But we are also getting 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. So 7 or 8 generally we're getting readings per second. So it's still going pretty fast. I'm not sure exactly how many readings per second Josip's routine used or got, but I don't think it's a lot slower. Okay, we've got to 35 minutes and I think I'm going to stop there. We will do all the other stuff next time. That's going to be writing data to disk. That's going to be all the other sensors, I2C and analog and so on. Now, while filming this video, we reached 1,000 subscribers. So, yay! And thank you so much, everyone who has subscribed. And if you have not subscribed, then please consider subscribing, because then we can have 2,000 subscribers, and that will be really, really good. And also this month, I've started off a Patreon. So if you want to help support the channel in that way, then the link is below. And I want to thank my first 2 patrons for joining up. That is really well appreciated, and their names will be scrolling by. And if you're in the top tier, then you'll get your name on every video, but regardless of what tier you're on, you will get early access to all the videos and ad-free access to all the videos, and there will be extras and Patreon exclusives. There's already one little video up there right now that is a Patreon exclusive. There will be other stuff, I'm not entirely sure what just yet, but you know, I'm open to suggestions. So until next time, thank you so much for watching. Please like and subscribe and do all the usual YouTubey stuff. Share it with your friends and comment in the comments below. And I'll see you next time. So, see ya. Bye.